hear me?
No.
No?
Not much.
Uh-oh. This is the max. What about now?
Yes.
Maybe the position here.
Yeah, maybe a little higher.
There we go. Okay, so what I had planned today, right, as it's written in the syllabus, was to discuss the exam with all of you. But as it happens, there were some of you who were sick and could not take the exams, so we had to do makeup exams. So I decided to have an exam discussion on Thursday instead of today. Okay, so on Thursday, we're going to distribute the exams and you're going to be able to do question by question if you have any. But any impressions in general that you'd like to pass on to me right now? What did you think? Easy? Too easy? Just right? Just Okay, so this is more or less the format that I think we're going to keep in the other two exams, so this mix of types of questions, right? But usually, I think the essay questions are great because most of you did pretty well, and it gives you more room to show how much you learned, right? So one thing I'd like to start commenting today is this means, I don't know, I already got some comments, but from the ones of you who I'm not sure you know. So October is an exciting month because October is when the Nobel Prizes in Science are announced. Right? So has everybody heard who got the Nobel Prize in Medicine or Physiology?
Some Japanese guys.
Who wants to know? Exactly, Ozumi from Japan, and this is really unusual because the Nobel Prize is always restricted to 3 people. So it's usually a big debate because sometimes somebody's left out and then everybody is just complaining and moaning, saying that somebody who deserved the prize was left out. But sometimes something happens and there's no doubt, right, that one person deserves it. And this is the case with Yoshinori Ozumi. And I remember very well how this went because it's very interesting for me because way back when I was an assistant professor, I remember a professor in my department asking, like we usually do, right, with young people we are mentoring, what are the areas in cell biology you are interested in that you would like to work on? And I remember telling him, way back, right, in the early 90s, and he just looked at me. He didn't want to discourage me, but he looked at me as if I was completely out of my mind. Because nobody, it was intractable. So people knew from electron microscopy that you saw these images of double membranes and then lysosomes fusing. So people knew this happened, and they also knew that it could be triggered by starvation. So when the cell sensed low amino acids, this started to happen. But there was no way of working with it. So what this group in Japan did, again using yeast genetics, so the major breakthrough was that he developed a very clever screen using yeast cells that he could then do mutagenesis and look at genes required for autophagy. And this opened the doors for an extremely active area of work. So the ATG genes, they are called. So there are many of them, and he has already, his lab and many other people mapped these ATG genes that he found initially in yeast, and then the orthologs were found in mammalian cells. It is now known that there are specific proteins that mediate each one of these steps. The first nucleation, the engulfment, and then the fusion with lysosomes. So this is a very well-deserved prize and illustrates very well how once you identify genes involved in the pathway, then it's possible to very fast expand it to other systems. So there are knockout mice, for example, now that are defective in autophagy. And they are mice expressing fluorescent forms of these autophagy proteins. And people really have learned a lot about it. So this is an exciting, very well-deserved prize. So what I want to discuss with you today, right? This means following up on the video you all watched, that Jennifer Schwartz, which is really what that modern cell biology can really be traced to the time in which we learned how to look at cells in more detail, right? So this cartoon here just illustrates how scientists use optical instruments on both ends. So there's very exciting developments. For example, you all probably heard of the Hubble telescope and how much was learned about the universe. And an interesting analogy is that there's always the next generation of instrumentation that allows you to see deeper, right? So the big discussion now, some of you may have heard that after the Hubble telescope that is in orbit and has really revealed a lot of detail on the galaxies around our galaxy, there's now the James Webb telescope that is going to be sent up in 2019, which really is going to be amazing because it's going to really push the boundaries close to the origin of the universe. So there's something similar happening in microscopy. So this is one image that Jennifer showed in her video, right? That it's possible now to use these fluorescent proteins of different colors. And over here, it's just mapping the distribution of neurons in a slice of the brain. And instrumentation is really being pushed very rapidly, right? This means the microscopes that are very expensive, that we spend a lot of money buying, something like 5 years, they're obsolete because there's something else coming out. So what I want to do is to give you a flavor of what is really happening in microscopy and why this is so important for the advancement of cell biology. So you all know, right, that light is electromagnetic wave, and over here you have the full spectrum that with the scale of the size of these amplitude of these waves. So going all the way from radio waves until gamma waves, which are really the smallest. And the visible light falls exactly in the middle, which this is the spectrum of colors, which make up visible light. So this is where we work with the optical microscope, right? What we call it the light microscope. So although light can be a confusing term sometimes, because in a way, all the electromagnetic waves can be called light. But the light microscope usually refers to visible light microscope. So this is a very useful diagram, right? Because it really explains the difference between the amplitude of these waves and which objects can be resolved by this type of energy. So, for example, what we see with our eyes is all based on this very large amplitude wavelength here, which is in the range of meters. And we can then start going now into the visible light and then ultraviolet and then the X-rays and gamma rays. And these waves are being higher and higher. And this then allows resolution of objects that are much closer to each other. So shorter wavelength is necessary when the objects are very close to each other, and these long wavelength type of light works if we only want to detect objects that are far apart from each other. So for cell biology, what really matters are these two ranges here of wavelengths, right? When we talk about the light microscope, most light microscopes that we have in our labs, they have ultraviolet, which is in the 360 to 400 nanometer range, and then the visible light that goes from 400 to 700. So the microscopes are equipped with filters and light sources that can produce these wavelengths. And then the electron microscope that we already talked a lot, right, with all the examples that I gave you before of the breakthroughs that happen in cell biology with electron microscopy. It's an electron beams that are used to bombard the samples, and they are much smaller. It can be between 0.004 and 1 this is another way of representing this, and this is a nice diagram to really show how limited is our vision, right? So what we can resolve with our naked eye is just more or less up to this level. Anybody wants to tell me, when in microscopy we talk about resolution, what are we talking about? What is resolution of an optical instrument?
I think it's like how well you can see the distance between, or how well you can see two separate objects that are actually separate.
Exactly. So how well you can distinguish, right? Two different points. So this is how. So what light microscopy did, right? Way back since the first microscopes that started seeing individual cells, allowed us to expand the power of our eye all the way to 200 nanometers, right? And this is the limit of resolution of the conventional light microscope. And then what the exciting thing that is happening these days is that there is the part 3 of the videos. I don't know, did any of you watch the 3rd video of Jennifer Schwartz? You guys didn't? So I didn't sign it because it's pretty complicated and dense, because it's an area that is in development still. That every year you get a new type of high resolution microscope. But it's a great talk for you to get an idea of how physicists are thinking of ways of expanding this resolution of light. So it has already happened with instruments that exist now, that they achieve, this is a log scale here, so they have achieved 1 order of magnitude from 200 nanometers of the conventional light microscope to 20 nanometers, meaning that objects that are 20 nanometers apart from each other can be separated as a sharp image. So you can basically see molecules and individual proteins. So, and this is still in development, and the expectation is that it's going to get even more powerful. And then, of course, we have the electron microscope that can go further, right? And we already saw several examples how we can really see structures in cells that are much smaller than that. So this is just to remind you, we already discussed this in class, the general diagram of the path of electrons in the electron microscope is that you have your specimen in a grid here in the middle, right? So there's a gun that shoots electrons, and there's, like in every microscope, you have a condenser that focuses this beam on your sample, and then you have something that is called a lens, but in the case of an electron microscope, it's a magnet instead of being an optical lens. So the purpose of this is, again, to focus the light and project it into a screen, which is where then it generates this kind of image. So the major principle of electron microscopy, like we already discussed, is the electron density. So basically, how the electrons are slowed down when they are being shot through this very thin section of the cell. Right? And of course, you have electron microscopes different power, but just as an example, if you have an 100,000 volts electron microscope, the resolution, so the structures that you can distinguish apart from each other, can be as high as 0.05 nanometers. So the preparation, we already discussed this, so the sectioning is critical. You need these instruments that can really make super thin sections, right? Because anything thicker than 100 nanometers are going to block too many electrons and you're not going to see anything. So the fixative is important. These are different fixatives that are usually used for light microscopy, but they work the same way, that they cross-link structures in cells. So the growth structure is preserved. But of course, a lot gets washed out because we are talking about fixation and then impregnation with heavy metals. One interesting variation, which is extremely useful in cell biology, is the immunoglobulin, right? So the image that I showed you before is the classical heavy metal impregnation, right? So this means you see here that the membrane so well, and also the chromatin in the nucleus, if you treat these sections, fixed sections, with these heavy metals like osmium or lead. So, but if you want to do what we call immunogold EM, is that we use antibodies that recognize specific proteins coupled to gold. So the gold is electron-dense, you can detect it with the microscope. So this is a great way to look at localization of proteins in cells at this resolution. The caveat is that most of the time, if you fix with these really very brutal types of fixation and dehydration, and then you also use the metals to increase the contrast, usually you destroy the epitopes, which is where the antibody binds. So the trade-off has been that scientists have developed ways to section these cells frozen instead of fixed, as they are lightly fixed. They are fixed with formaldehyde and a little bit of glutaraldehyde, and you don't put any metal contrast. So when you're looking at papers, right, and people are saying that they localize the protein, you can see these black dots. These black dots represent where an antibody against a protein that is being packaged on vesicles flooding out of the Golgi. So you basically can distinguish the Golgi cisterna here, and you can distinguish some vesicles, but you don't see it as clearly. And this is not because the scientists are just doing it badly. It's because if you put the metals to increase the membrane contrast, you're not going to get antibody binding. So immunogold usually looks like this. It's kind of more blurred, but it's still possible, especially in the good labs that know how to do this well, that you can still identify the structures based on morphology. So these are what we call frozen sections. And another really useful development, which is more recent than the microscopy, is the tomography, which we also already touched on briefly, right? So we're talking about these sections, right? They are very thin, but it's possible to get a block, right? The material is fixed, it's embedded in a plastic, and then you can make sequential sections. And then from each section, you get an image like this, and then what these instruments do is that they tilt the stage, and then you start getting images from different angles. And this is reconstructed computationally, and you get these three-dimensional images. So this is basically a three-dimensional image of a Golgi stack, in which each cisterna is basically stained with a different color. So tomography really requires a lot of computer power because you have to do a lot of processing. But this is something that recently gave me a lot of information in terms of three-dimensional structure. We talked also about scanning at the end, right? I think you all here said correctly that what scanning does is to resolve very well surface details. So instead of looking at the electrons that go through the sample, what it does is that you use something like gold that is very electron dense to coat the specimen. And these instruments detect the electrons that are scattered, emitted from the surface. And it gives really remarkable surface detail, right? The resolution is lower, right? Remember that electron microscope, conventional transmission EM can be 0.05 nanometers of resolution, and the best SEMs are between 3 and 20. And this figure here actually is comparing light microscopy on this panel here, showing that this structure here, which are these filaments in the hair cells of the ear that really move with sound, can be seen in a light microscope. But what you cannot see are these details, right? But you really can only resolve with the scanning. And this is what it would look like on transmission. All you get is the membrane surrounding it. You don't get much three-dimensional. So now moving to light microscopy. Right? So these things in light microscopy, it's not that different from the same principle of electron microscopy. If we follow the light source, right? So these microscopes these days are usually depends. You can have an inverted microscope with the light up top, or then you have the objective lens that then amplifies the image until it goes to the second series of lenses, which is what we call the tube lens, and which are associated with the eyepiece. So usually the rule of thumb when we are working with a microscope, usually what we want to know is how much enlargement your objective gives. So for example, say that you have an objective of 100x, and you have an eyepiece, an ocular of 10x, you're going to get a 1,000-fold enlargement of whatever you're looking at. Right? So this is something that scientists use a lot, and usually we have to put in all the publications what size of objective were you using and what was the enlargement. So the important point is already what we got here is this point spread function property of light, which is that whenever you have a point of light that is projected through a lens, it has this blurring in all dimensions, right? Because of course it's impossible to get an absolutely sharp image. And this is why the resolution is limited to 200 nanometers, because you can see here, this is the distribution, right, of a point spread function of regular visible light. So if you have objects that are closer than 200 nanometers, you barely can distinguish the two peaks, right? So this means the blurred area of one means the blurred area of the other one. And this is what keeps us from seeing things that are smaller than that. So this, another thing that scientists really pay a lot of attention to, so that this means this text here, this is also in your textbook, you can look into this in detail. But basically, these are the formulas that are used to calculate an important concept in microscopy, which is the numerical aperture. And the rule of thumb, the most important thing to remember is that, say you're shopping for a microscope, and the most expensive part of a microscope is always the objectives. And the higher the numerical aperture of the objective, the more resolution you're going to get, and importantly, the brighter the image is going to be. And this in fluorescent microscopy is very important. So this means everything is about capturing faint signals. So the cameras are also evolving really fast, so they're very sensitive detectors these days. But you still want to have a high numerical aperture objective, which is what gives the ideal conditions to improve resolution and brightness at the same time. And I think many of you who have worked with microscopes know that oil immersion is a very common procedure, right? And the reason that oil improves the quality of the image, it's all about the refractive index, right, of oil in relation to air. So if you imagine a specimen here, that is, usually we have this mounted on glass, right? So you have a glass cover slip, a thin layer of glass on top of it. And if there is any air between this glass and the lens on the path of the light, a lot of this light is basically not going to go through. It's going to bounce back. It's going to stay in its medium that has a higher refractive index, right, which is glass. So what putting a drop of oil does, so every time that you're in a microscope and you're putting the oil there and you do that thing that the oil touches and it forms a cone, what you're doing is that you're creating a homogeneous refractive index medium in which the light is not going to notice the difference between the glass and the oil, and it's going to go all the way through your lens, and you're going to get a much more efficient capture of the light. So again, this is a way of recovering, of seeing more of the light that you are shining on yourself. Of course, there are many variations. There are water objectives these days that are designed in a way that you can have everything in a water environment instead of glass. And there are many developments that for some applications are very good. So the types of light microscopy, so this can be a little confusing, right? This means this is a good example that you have a fibroblast picture that the same, absolutely same cell. That if you just look at a bright field, what we call bright field is nothing fancy. It's when light is just being sent through an unstained sample, right? So this is a fixed fibroblast, and the light is going through it, and you get this kind of image. That if a cell is very flat, you don't see much. So then the tricks are, right? It's possible to play with the slight variation in the phase of the light. So the light is going through the specimen. Right? In this case, it's not stained, so the only thing that is changing slightly the phase of the light wave is the structures in the cells, right? So the nucleoli, the more dead structures, etc. So there are microscopes that take advantage of this, and the two main types are either phase contrast microscopes or differential interference contrast. This is what we call BSCI. So this is another decision when we are buying microscopes, right? Sometimes you have to choose because it's difficult because of the optics and the attachments that you need, and you cannot have phase and the IC at the same time. So you kind of have to decide from which type of cell you're going to be working with. If you prefer to have this kind of detail, or if you prefer to have that. So this is one way of improving what you can see, and dark field microscopy takes advantage of something very different, which is the scattered light. So the light, instead of being sent through the cell, is sent in an angle. And then what the camera detects is the scattered light. So you basically get these light points in a dark background. So this is another way, depending on the application, that can be very useful. So what I wanted to do now is to really get all of you discussing, and I have one answer in mind, but maybe there are other answers that I would like to hear. There's no doubt that light microscopy is extremely powerful, and in a very important way, it's more powerful than electron microscopy, although the resolution is much lower. So why don't you start telling us, why do you think that there's such a big advantage to light microscopy compared to electron microscopy in terms of things you can learn? Yeah. Live microscopy. This is changed everything, and this is relatively recent. Most of microscopy was all fixed until recently. Right? So once the microscopes got good enough to look at it without fixation, you can look at dynamic things. So we can do what we call 4D, four-dimensional microscopy. Right? We can do it in 3 dimensions in space, and we can do it over time. So this is something that is moving very fast. And like I told you, the instrumentation keeps changing, and most of the focus right now, nobody's really making new electron microscopes. A lot of the effort is in making new high-resolution light microscopes, because this is the holy grail, to be able to look at a cell without fixing, without changing it. So these are examples here, right? This means, I don't know if you saw this video already. If you look, for example, a cell expressing a fluorescent protein, right? This is one of the things that light microscopy has allowed us to do.
EB1 is a protein that binds to the GTP tubulin cap at the growing ends of microtubules. Cells expressing a GFP-EB1 fusion protein reveal the spectacular dynamics of the microtubule cytoskeleton. Note that many, but not all, microtubules in this cell grow from the centrosome. Only the ends of growing microtubules are visible in this experiment. Those that are static or shrinking have lost their GTP tubulin caps and do not bind EB1. In contrast, when all microtubules are labeled with GFP tubulin, the true extent of the microtubule cytoskeleton emerges. Both growing and shrinking microtubules can be observed.
So think about this. At the end, I want you guys to have a discussion do this, right? So how do you get the cell to express PEG proteins like this, right, to be able to do this? So, but what is really exciting about a light microscopy is that, of course, you can do it without absolutely doing anything to the cells. So this is one example.
In this experiment, a bead coated with antibodies on the left is presented to a neutrophil held by a pipette on the right. The neutrophil quickly engulfs the bead by phagocytosis.
What is it, phagocytosis? I don't think that's
In a similar
synthetic
experiment,
words, but it's
a particle made of a chemoattractant found at the surface of fungi, like yeast, is presented to a neutrophil. Note how the neutrophil extends its pseudopods before it surrounds the particle and completely engulfs it.
So now it's going to be cool. They're going to move the source of the attractant.
Here, the particle is presented to the neutrophil and moved around. As the particle moves, the neutrophil senses the chemoattractant. Pseudopods retract and then protrude towards the new position of the chemoattractant. When the neutrophil finally contacts its target, it engulfs it by phagocytosis.
There's a great video I'll show you later in the semester of a neutrophil chasing bacteria. So this is just amazing. This means that they can absolutely shift directions and they're making a ruffling leading edge on one way and they completely reverse it. The bacteria goes to the other side. So this is really what changed everything, right? I mean, that people can manipulate conditions, for example. You can have these perfusion chambers in the microscope, and you can perfuse whatever you want, chemoattractants, you can put things on one side, and you can get the cells to go to the other one. So this is much more than we can do with any kind of electron microscope. It's that minimum perturbation. So of course, the light microscopy started with fixed cells. So this is the classical way that you can also embed in resin, like for electron microscopy. You cut thin sections, they don't have to be that thin. And then there's the classical staining. I don't know if any of you work in histology labs, right? This is something still used a lot in medical diagnosis, that you have these stains that stain differently, DNA versus cytoplasm versus other structures. So you get these different shades of pink and blue, which really are used a lot to stain structures. And for example, in cancer diagnosis, stains like this are still used. Pathology is very much based in very old, actually, approaches, which is how different structures and cells absorb pigments. But a more recent and extremely powerful application, of course, is the same thing that I mentioned to you that we can do on the electron microscope, right? Which is to come with antibodies against the protein that you're interested in, or it can be sugar groups also on other proteins, including lipids. And if you have your antibody coupled to a molecule that you can detect, the case of immunoglobulin, these antibodies would be coupled to gold. But in a light microscopy, what is used a lot is a fluorescent marker. Right? So this is a place where we spend a big chunk of our money in the lab is buying these secondary antibodies, what we call, because we can buy them in any color we want, and they're very pure and very specific. So you can stain different structures and cells in different colors. And what is really important so something like this, right? So this is a mitotic spindle in which you have two antibodies here, right? So one is recognizing the blue is not an antibody. It's this DAPT stain, which is a great stain for DNA. So you see here most of the chromosomes around on the pole. And then you have the microtubules with an antibody that's tubulin in green. And then you have specific proteins that are at the tip of these microtubules that are with another antibody. So what's really critical when you do this kind of fluorescence with antibody tags, that of course that one color doesn't spill over on the other one, right? So if this microscope was not able to detect individually these different colors, you would basically see everything, kind of a mix of red and green and blue. but this is exactly how these microscopes are designed, is to take advantage of this property of fluorescence that you heard in the video that Jennifer explained this, that fluorescent molecules, when they kind of jump to a different orbital level, right, when they are illuminated. And what happens when they come back to their ground state, that they emit a light that is of a longer wavelength, so a different color. So for example, if you illuminate a cell here with a blue spectrum of light, you end up taking green. And this is a really extremely useful property, because then filters, fluorescent microscopes are all about filters and how you can only let through one type of light, and then you can only detect another. Right? So let's see if I have the spectrum here. So this is a poster that most cell biology labs have this posted on the wall, because we have to know this very well. These are the different available colors of dyes that are used these days. And you can see here on this side at a wavelength that excite molecules, and what happens to them when they emit.
The term microtome, is that the name of the small sections that are cut out?
Microtome is the instrument.
Okay.
So it's kind of like a salami slicer, a very delicate one. Am I going too fast? Other questions? To give you nice time to discuss. So I think this is pretty clear, right? That since some of these colors have an emission spectra that are very close to each other, right? So you get this kind of distribution. So everything is about when you want to separate two things. So say that you're staining a cell with 3 colors, and you don't want the label to fall on top of each other. What you do is that you try to use filters that only get the peak of each one. So then you can separate. So this is very important to know when you go work on a confocal fluorescence microscope, because this is all automated, there's great software, but if you don't know how to set your windows, you can get bleed through, what we call bleed through, and it's just worthless, the result. So it's very important to keep in mind that you have to define your excitation and your emission line to get results that you can trust. And the design of the microscope, right, this means this is the basic scheme. There are many improvements these days, but basically this is how it goes, right? So if you have white light, it's composed of many different colors, and the first filter that you have in the microscope is the one that you set, so this is adjustable. So you adjust, in this case here, it was adjusted to a filter that only lets blue light. The other very important component is a mirror that it splits the light. And this sends it to a lens, right? And this focuses the light, and that's when it hits your specimen. And then this goes through a second barrier filter. So this barrier filter is going to be the one that is going to control the emission so quickly. Sometimes you can have more than one color going through, but this filter here is going to guarantee that what your eye sees on the eyepiece or the camera, of course these days we almost don't look at microscopes, it's kind of sad because it's all motorized and we don't focus by hand anymore, and these sophisticated microscopes, you have a very sensitive camera that detects the image at this point. So one thing that can happen in microscopes is when you put too much light, right, because you can adjust the intensity of the light. So what do you think? What happens if you just hit your specimen that contains a fluorescent molecule? What happens if you hit it with too much light? What can happen?
Bleach the fluorophore.
Bleach. So, and what does bleach mean? We use this term a lot, right?
Extinguish the fluorophore so you can't see it anymore.
So basically destroy the fluorophore. And this is a big problem. So this means when the fluorescent microscopy started, then it became something everybody was excited because you can do these movies and the cells are alive, but then you look for 3 minutes and the cell just looks like a blur, right? Because the fluorophore was destroyed. So of course, technical developments are always going on, and now there's a great microscope that is called the spinning disk microscope. So what this microscope does is that it has a wheel in between this path of the light that only lets the minimum amount of light go through. So basically it reduces, eventually you get bleach, but it extends dramatically the time that you can keep eliminating a cell before you get bleach. So this is again technical developments that there are many happening now that you can improve the time in which you can. It has reached a point that you can basically keep a cell fluorescence cell in the microscope for 24 hours instead.
The resolution of the spinning disk is less than confocal, right?
It is less, exactly. So there's always trade-offs, right? This is physics. The ones that you're interested in physics, you should really dig into this. But every time you change something, so for example, in a confocal microscope, you have these very sharp optical sections. The spinning disk microscopes are usually confocal, but a confocality is not that good. So you kind of lose confocality, and what you win is that your sample can tolerate more light for longer. Especially if you're doing live microscopy, sometimes it's worthwhile the trade-off. You have something right to this means so that's why it's so difficult these days, right? Because you really have to know if you're going to do microscopy or have friends that really understand this, because it's extremely expensive equipment, and they all have pros and cons. You can do one thing well, but you cannot do another thing very well. So this is one of the big problems we have at institution levels now, because it's impossible for individual scientists to own these instruments now in their own labs because it's so expensive. So we need these core facilities, right? So maybe some of you have already used these microscopes. So you pay a user fee, but it's still very expensive to buy the new one. So we always begging the dean, and can you give us a new microscope, because in 5 years the camera is not sensitive enough. And this is a problem because everybody wants to have that cutting edge technology, but this is very expensive stuff. Yes.
I just have one question. So sometimes you can change the width, or I guess the size of the cover slip. How does that affect the diffraction?
Right, so it's all about refractive index also. Right? So this means there are all these things. There are lenses, for example, that can see through plastic, which can be very useful because, for example, if you're doing microinjection, you actually have to see your cell in a dish. So that, but then these are usually not very high resolution lenses. And then you can use very thin glass, and then that increases the resolution because you can then use oil that really makes this smooth transition. So there are many additional tricks with this. I don't even have here, but maybe you heard of total internal reflection microscopy, which is the type of microscopy that the light comes from the bottom in an angle. So it almost does not penetrate the sample, but it creates this evanescent wave. So very thin slice that is emitting. So this reduces the kind of blur of the rest of the cells. So people can see, I think you can see this in your textbook. And it's one way of seeing individual molecules. The whole trick in microscopy is to reduce interference, because every time that you have an image formed, you're going to have blurring, and if you have a thick specimen, you're going to have blurring in many levels. So how do you keep this focused? Right? I think I have an example here. So one great development has been, there have been basically two ways in which people figured out how to deal with this blur. So this is a typical example. These are these very large, multiple strand chromosomes that some insects have, right? The pumpkin chromosomes. And if you just look at the DNA stain and look at just these chromosomes kind of squeezed behind underneath the cover slip, this is what you see, because there's so much material at all levels that you capturing the light at all levels, and you get this blurred image. So this is what a conventional fluorescence microscope would do. So then the computational power that is just increasing very fast. Now there are microscopes that really calculate, right? So this means the point spread function is how much a point of light on that instrument is going to diffuse in all dimensions forming the blur. So since it can be predicted, then you can process the image and you can remove the blurring that is predicted to happen at each light. So images are taken up and down, right, in what we call a C-section, and then the blur is removed by processing. Which is another thing that is a huge point of discussion, and we can come back to this, right? That it really touches on ethics in research. So it's very important to really know what processing is doing if it's not interfering with your conclusions, because it's becoming easier and easier to manipulate images and to take out components of it. But you have to really know that what you're taking out is just the blurring, and you're not creating any structures, or you're not losing any structures by this. So there are commercial deconvolution microscopes now that do this very well. And the other way of doing this, right, that is around actually longer than the deconvolution software, is the confocal microscope. Many of you probably that have worked with microscopy have heard of this. Our imaging facilities all have confocal microscope, and the whole basis of this is that to avoid this problem, right, in which the light in each section of your specimen kind of diffuses and you get the blur. You get your light first from the laser, the light source, to go through a pinhole. So a very thin pinhole that can be adjusted. So you just, and then when this is sent to your specimen, the light that is emitted also goes through a second pinhole. So the pinhole only allows the very sharply focused light that came out of that optical section, and blocks the light that is coming from the up above or below. And this is how you get sharper images. For example, right? This is a classical example. This is what you would get on a conventional microscope, that is just a blur. And then if you do these sections, optical sections, blocking with the pinhole the excess light that is being scattered, you really see the structure sharper. And this here, that's why the convolution actually came afterwards, because people got confidence with the confocal microscope that this is real. On the confocal microscope, you can directly acquire these sharp images. And then people figured out, well, maybe we can just mathematically remove what is being blocked here in the confocal microscope. And it's a cheaper microscope, actually, than the convolution. So, but it's very different principles. So then Jennifer spent a long time talking about this, right? The revolution that was GFP, this jellyfish fluorescent protein that has this really great shape, that it's very compact and it's kind of easy to attach different proteins. And this was the tree they got the Nobel Prize in Chemistry. One identified this jellyfish protein, the other one learned how to clone it and express it in other cells. And what Roger Chen did is to really develop this rainbow in which he started tweaking with the chemistry, the groups of GFP, and he made several shades of GFP, and then he started working with yes, red, Martoro, that he could also make the whole range from yellow to red. So this is basically how that rainbow pattern that we saw in the beginning, that Jennifer also showed in her video, that you can get these GFPs for the shape that you want. And you just couple it to your protein, you express it in the cell, and you can then tag different proteins and you can distinguish one from the other. So this was a big advance. I'll just mention to you a few of the other methods that I think the video explains very well, right? So this means it's kind of important for you to recognize these acronyms, which they are confusing. So what does FREP?
Fluorescent recovery after
Is that right? So that's a technique that we call FREP. You come with a light and you bleach out, right? Using this component, you just kill the fluorophore, in that area in which you put in a lot of light, and then you wait for the molecules to diffuse back in. And Jennifer discusses this very well, and you can do those very nice quantitative measurements of diffusion of proteins, if they're diffusing freely, if they are kind of in complexes with other proteins, etc. So that's FRET. Then you have photoactivation, which is the opposite. So this is another technical development in which chemists really figured out a way of only after you illuminate a molecule, you make it. So there's GFP now that is not fluorescent. But when you hit it with light, it becomes fluorescent. So it's kind of the opposite of FRET, right? That you can look at what happens to this group of molecules that were here over time. So this is all being done in live cells, right? So start thinking about this. So this is being done in live cells in which this GFP was attached to a protein that you're interested in for. So does this have consequences for cells? And then the last one, right, this means this one here is FRET, which I'm not going to ask because it's written right here, which is FRET stands for fluorescence resonance energy transfer. So this is a way of really estimating the proximity of molecules. So you tag each molecule with one fluorophore that emits in a different wavelength. And it's possible to then, what you detect tells you if they were close enough, so you are having this resonance energy transfer, or if they were far apart enough. And these distances are known for these fluorophores. So this has given great information on protein-protein interactions. One exciting way that is more recent, and there are different versions of this coming out all the time, but it's what we call the split GFP. So, right, I told you that there's already GFP of different shades of green. There's GFP that is not fluorescent, and you activate it becomes fluorescent. And there's GFP that is not fluorescent because it's missing one of the chains that makes it this contact folder structure. So you can attach this sequence that makes this extra helix of the beta barrel of GFP separately on another protein. And when you see fluorescence, you know the two things match. So this is something that is being used a lot in, for example, development. When you have really volume development and you don't know exact moment when some signaling molecule activates receptors. So people are using things like this, and they just, when they see the fluorescence, they assume that this is when the two proteins come together. This is proving to be easier to use than the one that I showed you before, the FRET. The FRET takes very precise measurements in the microscope, while the beauty of split GFP is that it's an forward fluorescence. So I'm not going to get into the details of super resolution fluorescence, but some of you saw the third video of Jennifer, so she goes into detail. There's several types that people are still figuring out what is the best approach. But this is what's happening. So far, it's still to the point in which it works better with fixed samples, although she tries to sell that it's possible to do it in live cells, but it's not that easy yet. So for example, this structures like chromosomes that appear like this blurred, this is the kind of resolution that you can get if you process it on one of these high resolution light microscopes, and since the individual strands of the chromosomes can then be identified, they color-coded them here. So you can get, for example, instead of waiting for the chromosomes to condense, right, a classical way of doing what we call the karyotype, that you want to see if the cell has all the chromosomes. So with this type of microscopy, you can do it at any stage of the cell cycle, because you really can see each strand, and you can figure out where there's software that tells you when it's getting and one of the strands. So this is still in the works, and the holy grail now is to get super resolution that works in live cells at the reasonable speed. still a little slow the way it is right now. But anyway, there was right, one level magnitude change. So there's already a resolution of 20 nanometers, which is really remarkable. So this gave the Nobel Prize in Chemistry just a couple of years ago. So what I wanted to know do now in these last 15 minutes is that in your groups, I would like you to think about this question, right? So you watched the video, you heard all this version of the power of fluorescent tags, but everything has pros and cons, right? So what is the major problem? I would like you to discuss in your groups and come up with one thing, right on the board. What do you think is the one problem that maybe you cannot trust all the results that you get with the fluorescence microscopy, and then we can discuss more. Okay, so don't think of a long, complicated list. Try to come up with one thing that could be a problem.
I love these. I like these kind of group thingies because don't actually listen to the lecture. What do you guys?
This is like in the quiz. This question? Yeah.
No, I saw.